would start with a real chemical process. And we're going to look at ammonia. Ammonia is a critically important industrial chemical, and also what you find in your household for cleaning. So it's a good example to start from. It's also really has some simple chemical reactions that make it an easy problem to work with. So ammonia, what's the formula for ammonia? This is NH3. So one nitrogen atom and 3 hydrogen atoms. This is our source for nitrogen. Where's the source for nitrogen for your body? Where do we get nitrogen from? Proteins, right? So proteins have nitrogen in the amino acid backbone, so we eat plants and animals and we get nitrogen out of that. For industry, we most commonly get nitrogen out of NH3 from ammonia. That's the easiest way to buy that atom off the shelf and plug that into chemical compounds. Okay, so this is a basic commodity chemical. Let's see, where is it in nature? So in nature, yeah, where's nitrogen in nature? In the ground, in the atmosphere, yeah, so in the atmosphere we've got lots of nitrogen. In the grounds there's nitrates and nitrites and what else? NH4, there's the ammonium ions in the soil, and let's see, there's a whole nitrogen cycle in the environment. How does nitrogen get from the air into the soil? Precipitation. Bacteria. Rain, bacteria. Yeah, so it gets fixed by bacteria. And how does it get back from the soil? So there's trees. Okay, terrible artists. So the trees are going to take up the nitrogen from the roots and the plants, and then the animals will eat the so the animals will eat the plants, the animals will produce animal waste, and that will cycle ammonia, nitrogen back in, and then when the animals die and decompose, that will cycle nitrogen back into the soil too. So we have this whole cycle of nitrogen in the environment, lots of nitrogen moving around. So then we've started to become a major part of this cycle. So the ammonia, the global production of ammonia, 1.6 times 10 to the 11th kilograms per year. That's a lot of ammonia we produce. This turns out to be 27 kilograms per person, for every person on the earth. In the U.S., production is 10% of the global. We're doing 1.6 times 10 to the 10th kilograms per year of ammonia that we make right here in the States. That turns out to be about 50 kilograms per person. So in the States we're 50 kilos. That's about your own weight in ammonia that we're industrially manufacturing every year. So this is a pretty important chemical. We make a lot of it. How do we produce it? What would you make ammonia out of? Where's our cheapest source of nitrogen?
Air.
The air, right? So the air is almost 80% nitrogen, so that's a good place to get it from. So we need nitrogen from the air. Where are we going to get the hydrogen from? Water. Now what? Now we've got oxygen. So what else are we going to do? We're also going to add natural gas, methane. Methane, natural gas, methane nitrogen and water we're going to use to make NH3 and CO2. So natural gas, nitrogen and water, make ammonia, and the byproduct. Can we balance that equation? Let me do that real quick. Take 30 seconds, verify your answer with your neighbor. When I say that, that means I'm going to call up
4 nitrogen gas, 6 water, and 8 ammonia, and 3 carbon dioxide.
So it is a little more complicated than usual, right? Usually we have 2 things maybe going into one. If we think about the atomic scale, how would a reaction like this happen? 3 molecules of methane bump into 4 molecules of nitrogen at the same time, bumping into 6 molecules of water, and then they all rearrange to give 8 of ammonia and 3 of carbon dioxide. Does that sound good? Yeah, all of these molecules coming together and bumping into each other and rearranging. The physical mechanism, I can't really picture that happening. This is not a real process. This is a balanced chemical equation with some things going in and some things going out. This is not necessarily the steps to make this happen. If I take natural gas, so I can get that at home on my stove, water, I can get that out of the tap, and nitrogen, I can get that out of the air. So if I put all that in a box and shake it up, am I going to make ammonia? No. Why not? Yeah.
You might need like a catalyst or heat to make it go
Catalyst, heat. It might not even be lower free energy on the right side. It might spontaneously, I don't know which way it goes. I might have to calculate some free energies of each to know about that. Okay, so besides knowing what we want, then the real skill of a chemical process engineer is to figure out how would you actually make this. Process that we do this most often by right now is called the Haber process. It's named after Fritz Haber. And he did this in 1909, right as the chemical industry was starting to grow. And then he actually won the Nobel Prize for this. He actually won 2 Nobel Prizes, 1918 and again in 1931. It's recognized as a big deal even back then. This process makes ammonia that feeds about 1/3 of the world's population. So that's pretty important, and I can't believe this statistic, but I've seen it a few places. Half of the protein in our bodies, in human bodies around the world, half of the protein in our bodies, that nitrogen atom came through the Haber process at some point. So we've processed a lot of nitrogen atoms to make ammonia, to make fertilizer. What we're basically doing is supplementing this process, putting the ammonia in the ground as we're doing our industrial agriculture, or pulling a lot of crops. We deplete the nitrogen in the soil, we've got to replenish it. So most of this stuff gets used for fertilizer to grow crops to feed us. So yeah, it's a pretty important process. Fritz Haber has an interesting story. There's a bio sketch of him in the book. I'd look for that and read it. He did some pretty amazing chemistry. He's a pretty highly driven person, but then there's a lot of German chemists in this era that got tied up with the Nazis and ended up with a bad end, so I won't spoil the suspense, but it's worth reading the story in the book. Okay, so there are three steps to the Haber process. Step 1, steam reforming of methane. So we'll take CH4 plus H2O. We're going to make carbon monoxide and hydrogen. So this is endothermic. Let's do it at high temperatures. We need to use a nickel catalyst. This is the kind of magic that Fritz Haber worked out. And to be honest, I don't know how you guess at this stuff. I think you kind of try some different things, put some things together. I'm not a chemist, so this is not specialty. So the second step is called the water gas shift reaction. Here we're going to take carbon monoxide that we got from the first step. We're going to add more water. We're going to get CO2 and more hydrogen. The whole idea here is we're making the hydrogen to get that hydrogen atom for the ammonia. So this is mostly exothermic. The first one I'm going to put energy in, the second one we're going to get energy out, and the third is called the Haber. I call the whole thing Haber process. It's the Haber reaction. And we're going to take nitrogen now, add hydrogen, and take it straight to NH3. Put those two atoms together. This is strongly exothermic. So a lot of energy up there. We're going to do it at high pressure. We're going to push those atoms together. Medium temperature. And iron oxide catalyst. Troy, why don't you give me the first one?
Just add 3 on H2.
3 H2s. I want the second one.
It's already done.
It's good. The third one.
3 H2, 2 H3.
Any disputes? Great. Okay, this is much easier, right? Okay, so we have 3 reactions. And at the end we can get an H3. So the next thing I want to do is talk about how we put the 3 pieces together. So I have 3 separate reactions. So as a chemical engineer, we might think about doing these in 3 steps. 1 reactor, second reactor, a third reactor. First reactor, I've got 3 different sets of conditions that I need. I also am going to get some byproducts of CO2 that I'm going to have to take out. I might want to do that before I do the third reaction. So I'm going to start piecing together the parts of this reaction. So the thing I want to do is find out how these 3 relate to each other. And we're going to do that with a technique called a generation consumption analysis. So this is a method to synthesize reaction pathways with multiple reactions. And then when we put these together, what are the goals we want to do? We talked about this a little bit on Monday. We want to make the most product or products out of the least raw materials and with the least byproducts. How am I going to do that? We're going to do a few steps. The first step is to write balanced equations. Second, I will list all I compounds in a table. So we're going to make a little table to analyze the system and see what the best way to run the process is. So I want to make a list of each compound. CH4, H2O, CO, H2. CO I already have, H2O I already have, CO2, H2O I already have, N2, H2, I already have NH3. Reaction K, I want to write new IK for each compound in K columns. So how many reactions do we have here? 3 reactions, so I'm going to make 3 columns. Reaction 1, reaction 2, reaction 3, and I want to get new for each of those compounds in each of those 3 reactions. So reaction 1, CH4, what is new of CH4 in reaction 1? New CH4 in reaction 1 is, how many said 1? Okay, go. How many said negative 1? Okay, so that's a -1. H2O. Go ahead, everybody. -1 CO, +1 H2, 3 CO2, 0, 0, 0. That's it, that's what we're doing. Okay, reaction 2, CO, -1, H2O, -1, CO2, 1, H2, 1. Great. And these others are zeros. 0, 0, 0. Column 3, nitrogen, -1, hydrogen, -3, and ammonia +2. Zero, 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 zero. And then I can add up and get the total compounds that I would either consume or produce if I did 1 mole of each reaction. If we did all 3 reactions, we add these up. -1, consume 1 mole of methane. We can consume 2 moles of water, 0 moles of carbon monoxide. Everything I make in reaction 1 we consume in reaction 2. Hydrogen, +3, +1, -3. We make 1 hydrogen, 1 mole of hydrogen net. Carbon dioxide, make 1 mole of carbon dioxide. Nitrogen, costs me 1 mole of nitrogen. And ammonia, make 2 moles of ammonia. So step 4, sum up each row. New I net equals the sum over each reaction K of new IK. So we took that matrix, new IK, this is a matrix, right? This is a new IK, this matrix. We just took the sum across each reaction K to get for each compound I, what's the net production. So what are we trying to do? We're trying to make, what are you trying to make here? Ammonia. What did we end up making? Ammonia, carbon dioxide, hydrogen. Hydrogen might be okay. Maybe eventually we can put that in our cars and fuel our car. Carbon dioxide, is that any good? If you're a plant, maybe, but we haven't so much of that. So, yeah, so we don't really want that. So the idea of the generation consumption analysis is then to balance out this matrix and the multiple steps in the process to be more efficient. So this looks like a byproduct. This looks like a byproduct. And we could make it a product. If we need hydrogen, maybe we're doing an ammonia plant next to, I don't know, a polymer plant, and we need to hydrogenate some kind of polymer. Maybe that'd be a product, and we'd sell it. we might get money out of it. But if we're just looking at this process in isolation, that's kind of lousy. So what do we do? Yeah,
I just have a question. If hydrogen is a byproduct, why isn't it in the original?
Yeah, it's not even in this original equation, right? We did the big balance. We shouldn't even have to make hydrogen. It says we should be able to get rid of it. Should be able to make it as an intermediate and then get rid of it. This is an overall net reaction. How can we get rid of it? What can we do with the hydrogen? We have extra hydrogen. What should we do with it? Just take it and plug in more nitrogen. Get rid of it, right? That's the common sense, or that, some of us think about, what will we do with it? Think about the common sense way. Maybe we'll just get rid of some nitrogen using intuition. The mathematics should lead us there too. So what we can do essentially is scale these reactions relative to each other. So I'm going to introduce what do I call it? A multiplying factor for each reaction. Chi1, Chi2, and Chi3. And step 5 is going to be able to choose those Chi3. So 5, adjust multiplying factors for each reaction Chi K to adjust the net consumption and generation. So we're going to change our equation here. VI net equal a sum of a multiplying factor chi k dotted with mu I k. Because each of these reactions stands on its own, right? I can run 3 times as much as the bottom reaction if I want to, as long as I get the feedstock. So I can take, as long as I multiply these all together, that's valid. So should have left an extra line up here. Chi k. So what we had up before was essentially just multipliers of 1. This was our naive total. This is our smarter total. Net. Okay, so what would I do? So I can do some math to figure it out. So Anna pointed out, why do we even have hydrogen? We shouldn't have hydrogen. Well, we can get rid of the hydrogen by using our equation there. Get rid of it. I have to kill this. So the hydrogen is going to be H2 balance. H2 net is going to be 3 times Chi1 plus Chi2 minus 3 times Chi3. Here I'm going to put 1, 2, 3. Then I want to have no net hydrogen, so I can set that to 0. I've got 3 equations, 3 variables, Chi1, Chi2, Chi3, 3 equations would be nice, so I can specify something else. What else might I want to specify? See, our other byproduct is CO2. Can we get rid of the CO2? How many think yes? How many think no? Yeah, there's no other reaction to get rid of it. I'm making it a reaction 2, there's no reaction that consumes it. So for this choice of pathways, there's nothing I can do about it. CO2 is going to be equal to whatever we put Chi2 at. What else? CO. CH4 is a reactant, that's reactant. CO, what's CO? It's another intermediate. Do we want to produce any CO? No, so let's get rid of the CO. CO net equals Chi1 minus Chi2 equals 0. That's helpful. And then third equation, well, I actually need to set a basis. So let's set a basis. Let's do the NH3 because that's what I'm concerned about. NH3 net production equals 1 mole. So let's try to get this one equal to 1. So if we did that, that's going to be just 2 chi 3. Then we can solve. So that tells me chi 3 is 1/2. This tells me chi 1 equals chi 2. And then that first equation, let's see, chi 1 equals 2. So 3 chi 1 plus chi 1 minus 3 times 1/2 equals 0. I've got 4 chi 1 equals 3/2. Chi 1 equals 3/8. And chi 2 will equal the same thing. So let's put 3/8 here. 3/8 here. Now how much CH4 do I take? 3/8. Reaction 1, and I'm taking up 1 mole there, so that's actually going to be minus 3/8. H2O, I'm going to take up 3/8 mole in the first reaction, 3/8 mole in the second reaction, so it's going to be minus 6/8 or 3/4. CO, 3/8 minus 3/8, there's my net 0, that's good. H2, 3/8, 3 times 3/8. Yeah, okay, let's see, 9/8 plus 3/8 minus 3/2. Well, it should be 0. CO2, 3/8 there, and 2 minus 1/2. Going fast now. NH2, 2 times 1/2 is 1. Any questions? Did I make any mistakes? I usually do. Okay, so some of the good things I see is there's no byproducts here. I have my product here. Got another product here I'm not as crazy about, CO2, what are you going to do? And then I've got the reactants here, here, and here. And I should be able to then take these numbers and rewrite them into an overall reaction. Should be able to take minus 3/8 CH4 minus 3/4 H2O and minus 1/2 nitrogen. And that should go to 1 NH3, how much CO? CO2, 3/8 plus 3/8 CO2. That's those pluses because those are reactions. And that should be the same as my overall reaction. Did we get that right? Okay. Okay, any questions on the generation consumption analysis? Show you a couple more. The thing is, you notice this is kind of tedious. This is, you don't want to do this for, ammonia is okay, there's 3 reactions and like 6 species, but you really don't want to do this on your own, on paper. What you want to do is get a spreadsheet, put your 3 reactions on top, your compounds on the left, your chi-Ks across the top, start filling in numbers. This is what it should look like at the end. What else? You can guess on the chi-Ks, you can use equations on the chi-Ks. Okay, great. You should be using formulas for this. I'm going to add up -1 times chi1, 0 times chi2. The dollar signs, what does the dollar sign mean? It's absolute reference, so I should be able to copy this formula all the way down. Tiana will be looking for that in your spreadsheet, so you should be able to copy that down. Everything works. Try to make it neat. A few boxes help straighten the eye and help it be easy to read for someone to see. Use of bold and underlines. It doesn't have to be super amazing. We're not graphic artists, but I want it to be clear and easy to understand. Okay, the other examples that are in your book, so we're going to go through them really quick here, but you can get all the details in the book. Is the LeBlanc process for making soda ash. This is soda ash or sodium carbonate. Pretty basic chemical, just sodium and carbonate. Carbonate salts that make up a lot of the Earth's crust. Sodium is also a lot of the Earth's crust. It's pretty basic stuff going around. Used as washing soda, detergents, and a base. So this is a another pretty basic chemical. LeBlanc figured out how to make this stuff. 1791, LeBlanc. Sodium chloride, which is just salt, sulfuric acid, so to make sodium sulfate, hydrochloric acid, then take the sulfuric acid, add some carbon, which is coal, you get sodium sulfur, sodium sulfide, carbon dioxide, take the sodium sulfide, then exchange the ion with calcium carbonate, which you can get from chalk and long dead seashells, get your sodium carbonate and calcium sulfide. Identify any hazards or tricky materials in this process? HCl, what's that? Hydrochloric acid, you've done that in the lab, treat it with care. It's an acid, it's corrosive. Chlorine is very reactive. Anything else? Sulfuric acid, same thing. Anything else? Yep. Coal is non-renewable, and it's, you dig it out of the ground, it's pretty dirty. It's got nitrates and sulfates and all kinds of other things in it. When you dig it out of the ground, especially in 1791, lots of messy stuff in here. So you could do this. You could do a net-gen consumption table. This is a picture of a town in the UK in the late 1800s. It's not a pretty process. Some of the dark days of the chemical industry, leading to a lot of environmental regulations. So this was also the start of people saying, hey, we should do this in the right way that doesn't make it miserable to live around. Here's the LeBlanc process. I'm trying to get them to make the screen bigger so we can all see. All right, let's see. So red are things we consume, blue are things we make. We're trying to get sodium carbonate. We make a mole of that. We also make a mole of calcium sulfide. We make 2 moles of CO2. We make 2 moles of hydrogen chloride. So we make 2 moles of hydrochloric acid, which is dangerous stuff. 1791, probably just dumped it in the river. Killed all the fish, did a lot of nasty things. So later on, also in that picture you saw there were lots of chemical plants there. Later on they figured out, hey, we could use this for something else, and then you start closing the loop and making your own little industrial ecosystem. But it's costing all of these natural resources, salt, hydrogen sulfide, coal, lots of coal, and calcium chloride. So what's nice about this Gen Con analysis is it tells us what's going in and out and where the byproducts are, and then we can start playing with it. There's 3 reactions here, and they kind of have a cascade. These reactants make these 2 things, and we use that to make this, we use that to make this. It's really simple. From a chemistry standpoint, it's logical. But from a resource standpoint, a process engineering standpoint, it's not maybe the best thing.